welcome all of you to the session of heat transfer. In the previous lecture, we had derived the one-dimensional heat conduction equation, which is observed by the cylindrical surfaces, and we have applied that same formula for the composite cylinders also. And we have discussed that when these cylinders, there is a fluid motion inside these cylinders. That means the cylinders are carrying some processed steams or some processed fluids which is required for industrial purposes. Then we see that both the conjugate effect of conduction as well as convection takes part. So in those cases what we do is that we sum up the thermal resistances as the effect of both the conduction and both the convection. So from Fourier's law we can easily derive the thermal resistance because of conduction, and from Newton's Newton-Raphman law of convection, uh, or sometimes it is also called as Newton's law of cooling. So from that specific law we can derive the convective resistance. Now today we'll take two numerical problems and let us see how we have understood the theory, and I think it will uh, sharpen your understanding about the heat transfer, specifically conduction heat transfer through the cylindrical walls. So let us start with the first problem. So here you can see that an insulated steam pipe of 16 centimeter diameter is covered with 4 centimeter thick layer of insulation. The thermal conductivity of the insulation is provided here, and it is 0.9 watt per meter degree. Okay, and it carries process steam. Determine the percentage change in the rate of heat loss if an extra 2 centimeter thick layer of lagging whose thermal conductivity is 1.25 watt per meter degree is provided, given that surrounding temperature remains constant and the heat transfer coefficient for both the configurations is 12 watt per meter square degree. So I will draw a I will draw a figure of which will explain two cases, and I think with the help of that image you will understand it very sharply. So let us draw the figure. Okay, first of all I'd like to say that I am very bad. I do very bad drawings, so please pardon me. And but I would like to say that this drawings would be enough for you to understand. Now it is well mentioned here that the steam pipe has a diameter of 16 centimeter, which means that it will have a radius of 8 centimeters, and the layer of insulation is 4 centimeter thick. So obviously this is your layer of insulation. Okay, so it is quite obvious that it will be the outer radius would be 8 plus 4, that is 12 centimeter. And mm, in the second case here, this extra 2 centimeter lagging or insulation material has been provided, which means that R3 would become 12 plus 2, that is 14 centimeter. Okay, so now we have, and here if we consider this material has a thermal conductivity of K2, then this K2 can be written as 1.25 watt per meter degree Celsius or watt per meter Kelvin, whatever you wish. Okay, so now the question is that in the first case what is the heat loss, and in the second case what is the heat loss. You need to calculate that. Okay, so now how heat loss can be calculated. Now you need to know the temperature difference. Since the temperature difference is not provided here, you would expect that in both the cases the uh, temperature difference would remain the same. That means if this inner wall had a temperature of T1 and the process steam has a temperature of T0, then del T will be uh, T1 minus T0 in both the cases. So the temperature difference remains constant. It is a thermal resistance which goes on changing. So here you can observe that there will be two thermal resistances. So this is for this one, it will be a conductive thermal resistance, and the heat transfer, regarding the heat transfer of convection of this outer wall and the process steam, there will be a convective heat transfer. Here what will happen? Here there will be two separate conductive resistances. So for this one, which has thermal conductivity of K1, and for this layer which has thermal conductivity of K2. So here you will find two conductive resistances, and here this process steam has the convection heat transfer coefficient as 12 watt per meter square degree. So in this case, that means in the second case, there will be two conductive resistances as well as one convective resistance. Okay, now you need to do the mathematics. So you know, when there is conductive resistance, so let us deal with the first case. Okay, so we are dealing with the first case. So what will be the so I am writing conductive. Okay, so this is your conductive thermal resistance. Now what is the formula? If you remember, it will be 1 by 2 pi K1. I'm sorry. Just give me some time. I will clear it and write it in a better way. 1 by 2 pi K1 L multiplied by, so multiplied by ln of what? It will be R2 by R1, right? If you remember the formula, then this will be the conductive thermal resistance. Okay, so now you can find the conductive resistance, and now you know the value of R2 and R1. You don't know the value of L, so let it be, keep it as it is, and you know the value of K1. So this is the conductive resistance which is present in the first case. And now let us deal with the convective one. So R convective, so it is nothing but H0 at into the area. So what will be the area? So you need to consider this radius. You have the length of the cylinder as L, so the formula is 2 pi L. So 2 pi, that there is a R involved also, which I have missed. So 2 pi R3 R, sorry, I'm very sorry, there is only R2 and I'm writing, sorry. So it will be R2. So now you have both the resistances. Now we need to sum it up. So the total resistance, let us write RT. RT is nothing but 1 by 2 pi K1L into ln R2 divided by R1 plus, I'm just removing this word here, plus this one. So it will be 1 by HO 2 pi R2L. Okay, so now if we do the mathematics, if we take 2 pi L common, so you will find it will be like this: ln of R2 divided by R1 divided by K1 plus 1 by H0 So it will be 1 by 80 into uh, already 2 pi L is taken common here, so it will be 1 by 80 multiplied by R2. Now if you concentrate on this one, you can understand that we have all the data for this equation. That means you know R2 is 12, R1 is 8, K1 is 0 0.9, K2 you know as sorry, R2 you know, HO you know 12 watt per meter square. So you can put all the values here. So the equation ultimately can be written as like this: 1 by 2 pi L into it would be 1.149. Okay, so you can write 1.149. Okay, so I think you have understood. So please recheck the values, I would like to say, because sometimes there may be some problem regarding the calculation part. So please recheck it once. So I am just removing this part. Okay, and what I have obtained I will write. So we can write it will be ultimately, okay, so ultimately it will be 1.149 divided by 2 pi L. Okay, so pardon me if I have done it here wrong. So ultimately you will get this result: 1.149 divided by 2 pi L. Okay, so this is your ultimate thermal resistance for the first case. And you know heat loss. Okay, so heat loss can be written as the difference in temperature divided by the sum of thermal resistance. So you can write this formula, you can write as 2 pi L into delta T divided by 1.149. Okay, so you will get a result of 1.747 pi L delta T. Okay, so this heat loss is expressed in the terms of L and delta T, because in the second case we will express in the same way, so that it can be easily calculated. So our motive is to calculate the percentage change. So if these three terms they are present in the next case also, then easy to identify that these terms are alike terms, so it will not cause any problem while calculating the percentage change. So we have completed the calculation regarding the first case where we have calculated the heat loss. So just I would like to rewrite it once, and I will keep it safe here because we would require this value once again. So after just rewriting it, so now say how we can calculate the thermal resistances for the second case. Here I have already mentioned that there will be two separate thermal conductive resistances, and the third one will be of the convective type. So let us write R1. R1 is your first case, so it will be 2 pi. So it will be similar as it was in the earlier case, 2 pi. So you know the formula, 2 pi K1 L, right? So 2 pi K1, I'm sorry, so just give me some time, I'll rewrite all the formulas now. So as you can see, I have written the formulas for the three separate thermal resistances. So as you can see, the first two, R1 and R2, refers to the conductive resistances, and the third one, R3, refers to the convection resistance. Now it is quite easy to understand that here this insulation layer has a thermal conductivity of K1. Okay, so uh, if we consider the conduction between this wall and this wall, then it is easy to understand, easy to say that the heat transfer will take place via the mode of conduction, and the thermal resistance observed by the heat which is traveling can be written in this type. Okay, so this is the formula for the first one. And in the second case, when the heat is transferring in this direction, that means if we consider the heat transfer between this layer this layer to this layer, then the conduction thermal resistance can be written by this, because this material has a thermal conductivity of K2, and the conductive resistance can be written as like this formula. Okay, and this case, this is the convective resistance. Okay, so for the convective resistance we have to consider the whole radius, and there is a process steam which is moving. So because of the convection we can write this formula. Okay, so this is your convection resistance, and now we need to sum it all. And here you can see that we have summed up all the resistances. Two of them are conductive and this one is convective. So ultimately putting the values, we can say that we can take this common, 1 by 2 pi L can be taken as common, and here you get all the values, and you can put the requisite values and you get the net thermal resistance. So here you will find that the ultimate result would be, so I am just removing these things. Okay, leave it as it is. I will remove this part and this part also. So the net thermal resistance would become 1.1664. So I am once again saying that you need to recheck it once. Okay, 2 pi L. Okay, so now you have found out the thermal resistance observed in the first case, sorry, in the second case. So if you are interested to find out the heat loss in the second case, then you would write the same formula, that is delta T, the change in temperature, divided by RT, and we have already discussed that this temperature will not change. The temperature difference will not change for both the cases. Okay, so now if we put this value, then we will get that this heat loss in the second case becomes in the order of 1.711 into pi into L into delta T. So now you have got both the heat losses. Okay, so can you say in which case the heat loss is maximum? It is very easy to say that this has the maximum value. So in the first case the heat loss was maximum, and here the heat loss has been reduced. Okay, so you can say that the decrease in heat loss, the decrease in heat loss can be calculated simply 1.74, sorry, oh, we can write that QL1 minus QL2 divided by QL1. Okay, so pardon for my handwriting, but this is QL1 minus QL2 divided by QL1. So here it would be 1.74. so it will be 1.747. So this term can be taken common, and since you will see in both the numerator and the denominator this term remains, so this term can be neglected. Okay, so it is getting out of the equation. So 1.747 minus 1.711 divided by 1.747, and ultimately after the calculation you will find that this value is 2.6%. Okay, so because of the insulation, the 2 centimeter insulation which is provided in the second case, this helps to reduce the heat loss by 2.06%. Okay, so this is what the it was asked in the question. So we have found out the heat loss decrease as 2.06%. So it was very simple. You just need to calculate the thermal resistances observed in the both the cases. In the first case, since there was a single layer of insulation, there was only a single conductive thermal resistance, and in the second case, where there were two layers, there were two conductive thermal resistances, and in both the cases there were convective thermal resistance present. Okay, in both the cases it was present, so we had to add all the thermal resistances which were present during the uh, problem. So we just added up all of them in both the cases. In first case it was the sum of the convective and the conductive heat resistance, and in the second case it was the sum of two conductive thermal resistance as well as the sum of convective thermal resistance. And then using this simple formula, Q, which is equal to delta T divided by thermal resistance, the sum of thermal resistance. Okay, so this is the formula of heat loss. We calculated uh, both the heat loss in the both the cases. Okay, so we found that in the first case it became 1.747 pi L delta T, and in the second case it became 1.711 pi L delta T. Then we had to simply do a mathematical operation, simple algebra, and we reached the solution. So with this understanding, let us move on to another problem which will surely help you out to understand the concepts in a much better way. So here you can see that a steel pipe having an external diameter of 8 centimeter carries saturated steam at 40 bar and is lagged with a layer of material 4 centimeter thick of thermal conductivity 0.05 watt per meter Kelvin. The ambient temperature is 19.5 degrees Celsius, and the surface of the lagging has a heat transfer coefficient of 8.33 watt per meter square Kelvin. What thickness of lagging having a conductivity of 0.069 watt per meter Kelvin must be added to reduce the steam condensation rate by 50% if the surface remains unchanged. Okay, so it is the question here. You need to insulate it more so that the heat condensation rate reduces by 50%. That means it is quite obvious that you need to insulate in such a way so that the heat resistance, the net thermal resistance, would be twice. If the net thermal resistance becomes twice, then the heat condensation rate would drop by half, by 50%. That is what. So you need to insulate insulate it in such a way so that the net thermal resistance can be increased by 2 folds. Okay, so uh, you need to neglect the resistance due to pipe material and due to steam film on the inside of steam pipe. Okay, so now it is quite evident that this R1 would be 8 by 2 because it is the diameter, so it would be 4 centimeter. It has an insulation of 4 centimeter thick. So R2 would be 4 plus 4, so it becomes 8 centimeter. And the thermal conductivity of this lagging material or the insulation material is 0.05, which we have written here. The ambient temperature is 19.5 degrees Celsius, and the surface of the lagging has a heat transfer coefficient of, so this refers to the convective heat transfer coefficient. So we have taken it as HO, and this HO is 8.33 watt per meter square Kelvin. Now you need to insulate it further so that the condensation rate drops by 50%. So let us assume we have taken a layer of X centimeter thick insulation so that the net condensation rod condensation rate drops by 50% and the net thermal resistance becomes twofold or twice. So let us discuss the first case when we haven't applied the second layer of insulation. So there is only a 4 centimeter thick insulation layer present. Okay. So what would be the thermal resistance? So there will be two thermal resistances. So this is because of the first one, which is because of the conduction going on. So we can draw simply this one and this one. Okay, so this material has an thermal conductivity of K1, and uh, because of the heat conduction, okay, between these two layers, we can write this formula 2 pi, okay, we can write 2 pi K1 L ln R2 divided by R1. So we have used this formula a lot in the previous problem, and in the next case it would be nothing but the convective heat transfer coefficient. So what will be the convective heat transfer coefficient? It would be HO into A, the area in concern. Now while calculating the area, you need to calculate this radius. So if this is R1 or 4 centimeter, then this is R2 or the 8 centimeter. Okay, so this area can be written as 2 pi R2 L. Okay, so now if you put all the values here, you know that K1 is 0.05. You know the length is not given yet. So let us take this length as the variable here. So it will be uh, so it will be, after doing the requisite calculations, you will find that it will be 2.207 divided by L. Okay, and in this case, if we put all the requisite values, that means HO as 8.33, R2 as 8 centimeter, and you don't know the value of L yet, so keep it in the terms of L. It would be 0.239 divided by L. Okay, so you can say that the net thermal resistance, let us use a different ink here. So the net thermal resistance in the first case, okay, so when the second layer of insulation wasn't provided, so this refers to the first case when there was a single layer of insulation only, which was 4 centimeter thick. Okay, so RT1 will be 2.207 plus 0.239 divided by L. So we can write it would be 446 divided by L. Okay, so it is quite it is again the repetition of the first problem. It is somehow similar to the first problem which we have taken. Okay, so now the So we have calculated the thermal resistance for the first case. Now let us move on to the third case, where you need to calculate the thermal resistances when an extra layer of x centimeter have been provided here. Okay, so this is x centimeter thick insulation layer which is being provided in the second case. Okay, so now in that case there will be, it is again simple to understand that there will be two separate conductive thermal resistances and a convective thermal resistance. Okay, so this RT1 would remain the same. Okay, it is not going to change, it will remain as it was. Okay, and this RT2 will be now included. This RT2 is the second thermal conductive resistance, which is because of the heat transfer from this layer to this layer. Okay, so this is the net thermal conductive resistance because of the heat transfer, because of the conduction heat transfer between these two layers. Okay, so the net thermal resistance can be calculated as 2 pi. So we have we do understand that this this thickness, which the x centimeter of insulation layer which we are going to provide, which would reduce the heat transfer, the condensation heat transfer by 50%, has a separate thermal conductivity, and we take this thermal conductivity as K2, and you know that this K2 is 0.069 watt per meter Kelvin. Okay, so this length doesn't change, and this would be ln R3 divided by R2. Now this R3 has been taken as X by us, so we can replace this R3 and we can write as X. So X is the unknown here, and let us take the third thermal resistance. So this thermal resistance is obviously because of the convection heat transfer going on between the steel pipe and the saturated steam, and it can be written as 1 by A0 into A. Now here the convection area, the convection heat transfer area would change into 2 pi, it would be 2 pi into R3, right? So you know that we have taken this R3 as X, so because this is your unknown, so now you can calculate the formulas. Okay, so now you can sum it up, all the thermal resistances. These three thermal resistances can be calculated in the first case, and uh, then we'll see how it goes. Okay, so let us just sum it up, or just first rewrite this equation of which are of uh, so we'll rewrite this equation uh, by the availability of these terms. So we know K2 as 0.069. We don't know the value of L though, so we can write 2 point. We'll see that after doing the relevant calculation you will get this value. Obviously we can recheck it once because there are uh, so it is always recommended that you should always do the calculation by yourself, so that you can understand the problem and you can do the problem in the when the situation is really important, when it really matters. So that is a main point, you need to solve the problems by your own when it is required. Okay, so that's why you need to solve the problems, you need to do the requisite calculations, so that the concepts and the calculations become much more sharp. Okay, and here if we put all the values, then we will get 0.019 divided by R3. So this is your first case, this is your second one, and this is your third case. Now if we write So let us just remove this all. So it would give us some space to write the sum of all the thermal resistances in the second case when the extra layer of x centimeter thick thermal resistances have been provided. So let us write as the summation of RT2, which means the sum of all the thermal resistances when an extra x centimeter thick insulation layer has been provided. So you will see that it would become 2.207 divided by L plus 2.308. I am sorry, so it will be 2.308. I'm sorry, I have missed this L in both the cases. So uh, you can take, in fact you can take this L as a common thing, common factor. We can take this one by L, so it would give us this value. So 2.207 plus 2.308 ln x divided by 0.08. I think I need to rewrite this 0.08 plus 0.019 divided by this R3 is nothing but the x, which I have missed though. So it is the unknown. Okay, we have taken the R3 radius as x. Okay, so I am just clearing this. So now you have two separate thermal resistances. So this is the result of the two separate case. In the first case, you have understood that there was a single layer of insulation only, but in the second case you can understand through the problem that it is exerting an extra layer of insulation which is x centimeter thick. We have assumed that the second layer of insulation will be x centimeters thick so that the net thermal resistance can be doubled up, right? And it indicates that the condensation heat transfer rate would be reduced by 50%. So it is quite evident that this RT2, that means the sum of thermal resistances in the second case will be obviously double of the sum of all thermal resistances in the first case. So that means we can write this one as 2.2446. So you can understand that in both the cases this 1 by L is the common term, so it will be reduced, and you can understand that now we can write this equation as 2.207 plus 2.308 into ln of x divided by, so I am just writing the thermal resistances for the second case, which is 0.08. I am taking a lot of time regarding this handwriting, but I think that you have almost done your calculations, because I hope that you have understood the logics. So this is the main thing. The summation of all the thermal resistance in the second case would be the double of the summation of all the thermal resistances in the first case. So that is the main thing. I think if you have understood, so if you have understood that once, then you can do the calculations by your own. So 0.019 by x. So this is a bit of weird, that this equation is bit of weird, since it involves a algebraic term, as well as it involves a logarithmic term. Okay. uh, so there is an inverse of x and there is a ln of x. So this equation can only be solved by heat and trial, or you can solve this equation via using the scientific calculator. Okay, so using the scientific calculator, if you solve this problem, then you will get the value of x, and this x would be near about to 25 centimeter. Okay, so when you provide an insulation of 25 centimeter thick, it is only then you can observe that the heat transfer rate by condensation can be reduced by 50%. So I think I have said it so many times, you must have understood these things. The To reduce the steam condensation rate by 50%, we need to increase the thermal resistances by the twice times. Okay, so the thermal resistance would be increased by uh, double times or twice. So what we have done here, we have equated the thermal resistances in both the cases. In first case, it was the summation of one conductive thermal resistance and the summation of one convective thermal resistance. But in the second case, because of the second layer of insulation, which was x centimeter thick taken by us, we understood that there will be three total thermal resistances. Two of them would be obviously conductive and one of them would be convective. So we summed made the summation of all these three resistances, and then we understood that this summation would be the twice of the initial thermal resistances which we have found earlier. So we wrote this equation: summation of RT2 is equal to 2 into summation of RT1, and then by heat and trial or using the scientific calculators, we can get this value x as 25 centimeter. Okay, so I think you have understood the problem totally and completely. So I think by solving this by understanding the solution processes for these two problems, you can move on to the by doing the assignments by your own. So here you will find two separate assignments. The first one is for the one-dimensional heat conduction for the plane walls, and in the second case, so I think it is so I have given a certain time so that you can understand this, and afterwards you need to just take a snapshot of this assignment, or you can just pause it or do whatever you want, but I have given enough time so that you can understand these are the problems. So here there are four problems for the heat conduction through plane walls, and here you will find that I have given four separate problems which would uh, help you to understand this one-dimensional heat conduction phenomena through the cylinders. Okay, so I believe what we have discussed today, that would help you to solve all these problems. Still, if you face any kind of problems regarding the solution of this problem, so you know you can always mail me at okay, so this is my mail ID, arindam.mukherjee@dacc.ac.in. So with this note, I like to end this lecture here, and in the upcoming lecture we would discuss the one-dimensional heat conduction phenomena but it would be applied for the spheres. Okay, so first we will derive the equation, and then we would apply the electrical analogy concepts, and then we will see if there is a composite arrangement, and then we will solve some problem. So this will be the schedule of this session. So with this, let us end the lecture of today. So goodbye, see you in the next lecture. Okay, okay, goodbye.